The game was developed for PlayStation 4, and techniques discussed are meant to work with and enhance the existing effects and methods. We're going to see sample videos. Some of them are going to be in-game footage. Some of them are going to be debug footage to kind of show the effects a little bit better for the presentation purposes. We will, the techniques we're going to look at open doors to other kinds of effects, new kinds of effects. And this talk is not meant to just kind of show what we did, but really, try to inspire and some other use cases for the stuff we worked on, the stuff we developed. In Last of Us Part 2, we started using GPU particles, and they are commonly used in games. And you can check out the work by Whitley and Hilaire Iglios on this. And the idea is that we maintain and update the particle state on the GPU, right? And what that really means is that we have access to GPU data, right? So with this particles update, they can sample textures, for example. That's great. The other interesting thing, right, is that's important, is that usually it's kind of hard to synchronize CPU and GPU in a sense. We cannot, to read the GPU data from CPU is tricky to do it fast. And GPU particles have access to current frame data. That's the key, right? That the particles can, when they update, access the data that's currently being generated on the GPU. And what does that mean? And we're going to talk about that. The rain splash effect is one of the effects we're going to look at. Is a great example of where we used a variety of techniques described in this talk. And well, first of all, it's a lot of simple particles, so it's perfect for porting to GPU. Here's an example of a scene where we would want to spawn rain splashes on the surfaces, right? And there's uneven terrain. There are roofs and hoods of cars. They are curved, right? There's water. There's vegetation. So with traditional methods, we would have to be placing emitters, some sort of plane emitters, maybe on the ground and on the cars. Maybe we have emitters attached to joints for the character. All of that works, except it's time consuming and it needs adjustment whenever the geo changes. Ultimately you will end up with some splashes, floating on the surface while other splashes are embedded in the surface. That's not the best use of our time. So how about we try to automate this, right? So we can avoid manual placement, splash emitters, that would be amazing. Maybe we can render height map and then use on the same frame, but that would be extra expense, using height map to kind of tell us on the GPU where the surfaces really are. We can try to spawn them in screen space. And let's look at the information available in screen space. What do we have? We obviously have depth buffer, which allows us to figure out where, a position of a 3D pixel or pixel in 3D. We also have gbuffer that stores normals and albedo, material ID, kind of based on what your engine does. For temporal anti-aliasing, for example, we have motion vector buffers, and you might also have this buffer called object ID buffer that we actually have utilized for our other effects. In terms of screen space spawning, one way to do it is just to kind of pseudo-randomly spawn sample across the screen, and if we kind of land on pixels that are within range, we can compute a 3D position for that, and based on depth buffer, kind of like shown on the screen. And we can also discard certain points based on maybe a normal, direction of a normal, so we don't spawn splashes on kind of vertical surfaces or surfaces that do not point towards the rain direction. And that kind of gives, and we also can modulate the kind of probability of whether I'm going to accept the splash location depending on how far it is from the camera, so that we can try to kind of enforce a more uniform spread across the surface. As far as normals go, we for this kind of stuff, for this kind of simulation and screen space, we opted to just use the depth buffer normals, meaning that normals we compute from the depth buffer, and instead of reading them from gbuffer, because the gbuffer normals might have other frequency detail in there that just not going to be helpful in this particular case. Here's an example of how this can work, right? So we have particles spawning on surfaces, and they're spawning on characters, they're spawning on the cars, they're spawning on the ground. So that's great, right? That's exactly what we want, and this doesn't require any kind of work from the effects artist on just setting up anything in the environment. So that's great. There are issues with it, of course. One of them was ghosting behind a moving character. So if our character is moving forward and we spawn splashes, they will kind of stay lingering in the air if we just spawn them and do not move them. And the problem is it's very hard to move them because we spawn splashes on pixels, right? And by default, when you spawn on pixel, meaning we spawn on, in 3D position, we don't know anything about what the surface we're on actually is. Like, it's the character, we cannot attach to it, it's just a pixel and ultimately a 3D position. So we wanted, kind of looking ahead into other effects we're going to talk about, we wanted to have some sort of a way to track, based on a pixel, to track position of a particle and try to attach it, but starting at the pixel, right? Without knowing anything else but just the pixel location, being able to track a surface we're on. So let's look at what kind of screen space information we do have that might deal with motion. And there's one, motion vector buffer, right? The motion vector buffer stores a 2D pixel offset to previous screen space position of a particular surface, right? So that's used for temporal anti-aliasing. It points backwards, right? So that's one thing that's important here. It points backwards, meaning we cannot use it directly, right? Knowing where the pixel was, where the position of particle was and pixel from last frame doesn't give us where that pixel is this frame, right? The mapping is actually backwards. So we cannot directly use it. But what can we do? Well, the thing is that the motion vector tells us how the pixel location is moving at this current frame, meaning where it was last frame, right? So we can use that to at least predict the velocity of the particle we just spawned, right? Or if we know the particle is sitting on a particular pixel, we can predict the velocity at which that pixel is going to be moved across, space to the next frame. So, and the idea is that if we use that velocity, we're going to move the particle and we're going to land somewhere based on this predicted position next frame. Of course, we're going to land somewhere that is not necessarily going to be correct, right? Because we are just, in other words, we're just using current frames information to predict what's going to happen next frame. And there's no way that doesn't give us anything about acceleration or deceleration. Right? If we were moving with certain velocity in the next frame, we slow down or speed up, the predicted velocity is obviously not going to have that information. We're not going to be able to move like that. So what can we do? We're kind of trying to, in this diagram here, it kind of shows, we had on one frame we had the particle kind of in the middle of the backpack. On the next frame, based on the predicted velocity, it lands like on the side of the backpack, at the edge of the backpack, and we're really looking forward on we're looking for something to correct it back to a correct position. So what can we do? Well, what we did was basically we used this predicted velocity to move the particle, and yes, we'll land somewhere, we'll land on a location. And we can check things like stencil bits and some position changes, some sort of thresholds for position changes. So like we can kind of more or less predict that the surface we landed on is still the surface of the object we were on. And then what we can do is, based on the position that we landed on, we can check, where was this position, this pixel last frame? And we can look at that velocity, right? And that velocity kind of gives us, okay, this is how much this particular surface is moving this frame. So we can take that and then re-simulate our particle motion. So in other words, we use predicted velocity to try to land on the same surface we were on before, right? And hopefully the deceleration is not too severe that we fly off completely and we land completely in a different location. That is possible, but hopefully it's not that bad, right? And so we land on the same surface, and then we use pixel motion vector at that location to figure out how much is the surface really moving this frame. And that, if it was accelerating or decelerating, like if the velocity is changed, that gives us the velocity of the surface, this frame. And we can take that velocity and we apply it to our original particle position from last frame and re-simulate the particle. Right? That's one way of doing it. It is not bulletproof. It is not exactly right, because just because that particular pixel was moving with one velocity doesn't mean that the whole surface was uniformly moving within the same velocity. There's rotation, there's deformation, there's other things happening. But it does give a pretty good heuristic for us. There is also another solution where we can kind of check the delta between this new location will land on last frame position of that. With the last frame position of our particle, we take that delta and we apply that to our new location we landed on. So that is another way we were trying to do this, but the first way I described worked a little bit better for us. That's the one we ended up with. So here's a video of kind of how it ends up looking if we use this prediction correction based on the motion vector. So you can see that now particles are, these rain splashes, even though they are fairly short-lived, they actually attach to the character pretty well, and they do not ghost behind, and they do not look like they're swimming. One thing would be, if we didn't do this correction, we would see the particles swim, and it'd be much worse and much more noticeable than the particles ghosting behind. So, and either one was unacceptable. So we needed to have this attachment. So that's great. So, and what are the benefits of this, right? The benefits are that this works on all geometry. Right, so we didn't work with skinned objects, we didn't look at anything like that. We worked straight up on just pixels and motion vector. It's all we did. And checking other buffers like stencil buffers and depth buffer, of course, for all of those two things are needed to kind of enhance this. So it's computationally cheap, right? It's very cheap, and it's in screen space. You know, it's all one, meaning it's just the cost. There's no loops or anything in the update. It works on static geometry, for example, with scrolling textures. That's pretty interesting, right? The geometry could be static, but as long as it's more writing motion vectors, this attachment will actually work. If there's actually some sort of something scrolling happening on the surface of geometry. It works on alpha cutouts, right? Because we're only looking at pixels and depth values. It's definitely not bulletproof. Not really a benefit. That could be a problem, right? This method is not bulletproof by any means. So we have to be able to handle possibility of losing tracking, right? With rain splash, it's not that bad because they're very short-lived, and if for whatever reason we lose tracking, we can keep the particle in the same location, just fade it out faster, and you know it's not bad. That's not that bad. So let's look at that example of we're talking about static geometry with scrolling textures. In this case, there's water here, right? The water geometry itself is not moving, but there is flow, right? Meaning the water looks like it's moving, right? Because it's moving in the shader, it's moving with the flow texture projected on top of this. And the cool thing about it is that our rain splashes move with that. Our rain splashes very well follow the flow, and you can actually see that the flow is it's pretty intricate. Like, you know, depending on where we are, what locations we are, you know, the flow is here, you know, in this location here is different than the flow here or flow here. And it's actually very interesting that you can even use these rain splashes almost as a debug for where the flow, you can see how the flow diverges actually into two different locations back there. So it's really interesting, and it's really cool that this particular effect and this particular approach just works. There's no special setup, there's no special, you know, parameters to pass in the flow textures into particle updates, nothing like that. It just works, which is a really cool kind of consequence of this approach. So let's look at some other things. Kind of staying within the same theme of rain and wetness. Let's look at, can we use this simulation in screen space? You know, so far it hasn't really been simulation, it has been more just spawning in screen space, right? And tracking in screen space. So what else can we do? Well, when it rains, we see trails of water on surfaces. And we also see droplets. You know, there's trails of water, and there's droplets falling off the geometry, on the edges, for example, of the geometry. So if we're looking at conventional solutions for these techniques, you know, we can bake some sort of drips and some sort of kind of water liquid drips into a texture, and then use some scrolling techniques to do that. That works fine. It does require some manual setup, obviously, and potentially lacks variability. And it's hard to instance that, right? Because, you know, if you have one car with certain direction baked, the drips baked, but then you have the same car on its side, flip on its side, it has to be different textures, you know, generated for that. So it does require some setup, and it ultimately looks fine with baked solutions. But we were looking for, can we enhance that? Can we make it a little bit better? And also, you know, we would need to have a separate setup for droplet spawns if we have things baked into the texture. You know, so how can we use this GPU attachment and the GPU particles to kind of enhance and maybe add a little bit more detail to this. Well, now we can talk about GPU particle ribbons, right? And the idea is that, okay, we could spawn one particle, like in the case of rain splash, we spawned this particle and rain splash lived on the surface. It was pretty short-lived, but it did live on the surface attached, right? So if we spawn multiple of those, of these kind of particles, and we connected them together, we could form a string of particles, which we call a ribbon, that are connected to each other, and maybe we can orient them based on the normal that we were sitting on, of the geometry we're sitting on. And that will give us a ribbon. And here's a screenshot of kind of what we would want. We would want to generate some kind of a ribbon that looks like a liquid drip, okay? And we can certainly do that with our attached particles, right? It's just the spawning now cannot be random. It's more like whenever you have a ribbon, if you have a root of a ribbon or a head of a ribbon, we need to spawn a new particle that's ahead of this head to become the new head of a ribbon. So we just kind of spawn particles and we kill the old ones and we spawn the new ones and we connect them together, and that looks like a moving sequence of particles like attached on the surface. They're not really ever moving, they're actually statically attached and they just track the surface, just like the rain splashes, but it gives illusion as if the whole ribbon is moving. It is a little trickier, right? Because now the particles are not independent. Now we kind of need to know information about our neighbors in the ribbon. And there also could be issues with whenever some particles lose tracking and now suddenly you have a ribbon that's disconnected. All of those things make it very, very complicated. And the easiest way to solve this is to store a ribbon inside of a wavefront where you can have cross-lane accesses to kind of pull the data from all the particles within the same ribbon. That is a huge time saver and simplification that makes these kind of maintaining these GPU ribbons much easier. Just like I mentioned before, the ribbons themselves, the particles themselves do not move. We just spawn new particles, kill old particles, and kind of this string of geometry is kind of moving forward. And they can follow gravity, of course, to, in terms of what is moving forward. Well, moving forward based on gravity, right? So if there's a head of a ribbon, we look at the normal. Based on the normal, we'll figure out where will gravity drive that particular ribbon. So here's how it would look in the game, right? So we see these ribbons spawning on the hood of the car. And, it just adds a little bit more detail. And the cool part about this, right, is that it follows gravity, which is really cool. It's unique always. It's kind of because it's spawning pseudo randomly, like in screen space. Who knows where it's going to spawn? We just kind of check for the normals and make sure it spawns in kind of in more or less reasonable locations. But the path of these ribbons will be kind of determined on the curvature of the geometry. And you see here how these two different ribbons they took a little bit different path, and that's because of just how the hood of this car is curved, which is that just adds more interesting detail. So just FYI, again, just reminder. Screen tracking can fail, and I want to mention it, right? The screen tracking on this motion based on the vector can fail. Of course, if we're talking about like static geometry, that's not as bad. And just to simplify the development of this, it's much better to store the ribbon inside of a wavefront on GPU for those of you who want to try to implement this kind of thing. In terms of rendering, right? In terms of like what do we actually render? Well. The best thing for us was to, when we render these particles, we just modify the G buffer, right? So as we render them into the G buffer, and that allows us to modify normal, roughness, and other things to make it more realistic, like water, and then let the lighting do its thing. So here's just a little debug video of how that looks. So this is the kind of final result, and then this is how it looks in the G buffer, right? The normals are being modified by these particles. Here's how it looks on the character. Right, so on the character we have same thing. Again, because it works on all geometry, it can work on a static geometry, it can work on a character. So you will see there are drips on a character happening on this leather jacket. So what else can we do? Well, if the ribbon cannot advance, let's say due to curvature, right, due to kind of getting to the edge of a geometry, and we can look at the rules of curvature, where the normal is pointing, the depth differences, to kind of more or less predict, okay, we reach some sort of edge of geometry. We can start spawning droplets, right? A droplet, just like a rain splash, can be attached to a surface, and it actually stays attached to the surface a little bit, it grows, and then it falls down, right? And that's all it does. And if it loses tracking, it just falls down immediately, right? So it's another one of those very effects. The droplets are very friendly to this screen tracking that can fail, but it's not a big deal because it's a droplet. It will fall down faster if it's not attached, if it loses tracking. If it stays attached, you will see it grow a little bit and then fall down. Either way, works fine. And here's a kind of debug video of this happening. You will see the character having all these drip simulations happening, and you will see, like, we have more droplets coming from her hair because there's so much curvature in there. The drips actually do not grow very much. They just kind of start spawning droplets, and you see these drips also happening on the body characters. So overall, really cool. And in this particular case, this effect was limited to just being on characters, the debug, the one that's enabled here. And it's really cool that it's all very cheap and it's all in screen space. And you can see how these drips dynamically change their direction depending on what the character is doing. And again, it's kind of a consequence. All these cool things are just a consequence of the fact that it's just done in screen space, and it just kind of moves on geometry. And so this is kind of the final view of this scene. Just to kind of reiterate, we have the rain splashes that spawn the character, stick to the character. We have the rain splashes that follow with the water. We have drips on the character, and we have droplets spawning on the character from those drips. And all of that just enhances the scene, right? All of this works with the rest of the effects, because the screen space is just screen space. It's just on the screen. We need to have other effects to traditional effects that form the majority of this, and then we have screen space effects that enhance this scene. Here's just another view of this. This is this character Abby now is now we can see the simulation of these drips on the skin as well, on the cloth. And again, the same idea of these drips spawning, and you will see very nicely how there's all kinds of droplets spawning in random places where the drips are kind of stopping, and it's going to spawn off her gun and off her fingers. Really cool details if you start looking closely. It just adds that another level of realism, another level of detail to the character. So the next logical step, because obviously we had blood on characters in this game, we wanted to use this liquid ribbon simulation for blood, right? That's kind of next step to enhance also the melee and cut wounds and shot wounds and things like that. So how can we do that? Well, the biggest issue, and again, to point out the problems with this method of screen space tracking, right, is persistence. It's only in screen space. If something is obscured by geometry, if you turn away, right, the screen space tracking is lost. So that's a problem, right? It's a big problem for something like blood, because you cannot have a bloody character, you turn away and look at them and they're not bloody, right? You can't do that. So what can we do? How can we deal with persistence? Well, the one thing about blood and how we use blood in dynamic blood in The Last of Us is that we have the idea of render targets, blood render targets, as in we have a UV mapped texture for every character that is a dynamic texture where we can render any kind of sprite in there, any kind of blood sprite in there, and it will show up on the character and it's used in the shader. Right, so whenever a cut happens or whenever we shoot a character, we just spawn a decal, basically it's a sprite, that is just a one single channel sprite that is rendered into our single channel blood texture. And that is going to be persistent because that texture is persistent. So the question is, well, how can we go from screen space, if we have some sort of screen space simulation for these liquid drips that there's blood, how can we go from that into UV space and ultimately to the render target, right? What can we do? So the issue is that the particles live in screen space. They have no knowledge of the object. They have no knowledge of meshes. They have no knowledge of what UV space the pixel is in, because the pixel is just a final pixel that was rendered. So we could try doing things like doing mesh raycast. If we were to use the new particle position and then the mesh raycast into that location to then intersect with all triangles of the mesh to figure out the UV, we could do that. It would be expensive. But we had object ID buffer, and that is something that an engine may or may not have. But an object ID buffer is a buffer that is rendered usually during depth pass that will per pixel store the information of which primitive and mesh this particular pixel came from. Right, so that means we kind of, from a pixel, we know kind of a mesh ID and a triangle ID, or maybe the vertex IDs, some way to know ultimately which mesh and which mesh index and which triangle did produce this particular pixel. There's obviously going to be a little bit of cost associated with rendering this additional buffer. Good news is that not all objects need to do that. In our case, we already were generating this buffer for other effects. And these techniques can show the usefulness of this particular buffer as well. So what that means, right? What does this buffer mean? That means if we have some pixel location, we know the mesh in some sort of mesh ID and a vertex ID or triangle ID, vertex IDs or triangle ID that generated this pixel, right? So we could have a little table set up based on the mesh ID and based on based on mesh ID, which object it belongs to, and ultimately, if that's an object like a character, what is the render target index, what is the vertex buffer, what is the index buffer, and all that. So we can reconstruct all that data. So what that means is that if we had a blood particle, for example, that spawned in screen space, we could convert that to UV space by, first of all, we check does the pixel belong to an object that has render targets, is the character, right? So we have a little table, we check, okay, this mesh index is in the table. Then we say, all right, well, what is the vertex buffer, index buffer? And then from the object ID pixel value, we figure out what is the primitive. We figure out the triangle, we put that into the screen space, and we project our pixel into that triangle to ultimately compute the barycentric coordinates. Then we use those and we read the texture coordinate buffer to ultimately produce the UV of that pixel in that character's UV space, which is great. That allows us to then know the UV location from a pixel location, and that is extremely important ability, right? And in fact, our liquid simulation blood drips, they do not really render, right? They do not really render themselves. Instead, what we do is we use them purely for simulation, and then we feed as we spawn the new particles, we feed that data to the CPU, and on CPU we have a special, we have the blood ribbons that live in the UV space of the render target, and then those ribbons grow, and those are the ones that actually render into the render target and produce this effect. So yes, so our screen space drips really are there purely for simulation, and that works great, right? So here's a video of a clicker being shot, and you will, of course, we're gonna on shots we're gonna feed in, we're gonna spawn like the baked artist-driven decals where we got shot, where this clicker got shot. But in addition, we will also have this additional simulation happening, and you will see that those drips will follow the gravity as expected, and that's just adds another more detail. That's more detail to these effects. In terms of spawning them, right? So we haven't talked about spawning, right? So with the rain splashes and rain drips, we were just sampling all over the screen space, and then just trying to, based on some probabilities, just spawn them, right? In this case, we cannot just spawn blood ribbons anywhere. If there's an original cut, there, how could we want the blood to only drip from that cut. We don't want blood start spawning in locations that are not bloody. So how can we solve that? Well, whenever there's an initial cut or initial wound from a shot, we know where that is, right? Because it comes from gameplay. So we can know which joint we can attach to, like a little box. We attach a little box to the joint. That is going to be our GPU spawner, right? That is going to be the general area where we could expect these blood drips to spawn. Then when we actually try to spawn them, we, again, pseudo randomly, we sample around this box, and if we land on that character, and then we can do a check for the UV location and ultimately for whether or not that location is bloody, right? So if we land on a character, we're like, okay, that's our character that we wanted. Let's convert to UV space. Let's look up that character's blood render target. And then that allows us to look up whether or not that render target is bloody at a particular UV space. If it is bloody, then we can spawn our drips, right? So our drips will only spawn within this box and only on bloody locations. And that's exactly what we want. One big issue with all of this, like it all sounds great while the characters are still. The problem is, like, whenever you're doing melees or shooting in a gunfight, the characters are moving constantly, right? And we only simulate in screen space, and that screen space information might just not be even available all the time, right? Here's an example. There's a character, and we're shooting them, and they're moving, like on a shot, they're moving, like, so it's not like the character is just standing still in front of the camera with the wound, in the view space. So how can we deal with that? How can we avoid that? Or not avoid it, but how do we deal with that? What do we do? Well, what we want to do is we want to make sure we maximize single frame information, right? What that really means is that when we actually do see the wound or the location where the ribbon is, and where we wanna simulate, instead of just like doing one update and moving one particle forward, just spawning a new particle to move kind of the simulation forward, we spawn multiple, we spawn many, and we call them phantom particles, but we really use only one, but we pre-spawn a bunch of other ones, okay? So in one frame, we're actually doing simulation for multiple frames. And next frame, if we have the information in screen space, great. We're gonna use the information to grow. If not, we're gonna use one of those next phantom particle available. That allows us to kind of, whenever there is information available in screen space, we're gonna pre-simulate a bunch and we're gonna start growing in that direction. And if we see that surface again, great, we're gonna readjust. If not, we're gonna keep those pre-computed particle locations. That is extremely important for this sim system, extremely important. Without it, this only really works on like dead bodies laying on the ground, right? Because anytime you shoot somebody, anytime there's a melee fight, the characters are moving constantly. You cannot expect the wound to be just there in screen space available all the time. So here's the example of this video of like a great example of this, the melee cuts happening on the character, and you see with time there is dynamic blood spawning on the character. We'll play this again. And that just adds more detail. It just enhances, using the screen space simulation, we enhance the visual look of this, right? If there was no screen space simulation, we would still have we would still have the cuts happen, right? We would still have the artist generated decals written into the blood map render target. That works. We can even have threshold textures and we had threshold textures to animate into the blood render targets. That all is great. We are talking about adding more detail with these techniques. We're not talking about replacing, we're talking about adding new techniques. So now the cool part about all of this, right, is that we have screen space information. So we actually have a lot of information available to us. In our case, we know, for example, skin versus cloth, and based on stencil bits or based on material IDs, we know that the pixel is the cloth, or maybe it's infected, maybe it's a skin, or we can add even more information to look up based on the object ID mapping and mesh ID ultimately. So based on those factors, we can, in screen space, we kind of read that data and we can pass it along to the CPU where the ribbons actually grow in the UV space. And that can give us different behaviors. So like in the case of this cloth, you will notice that on cloth, these blood drips, they start out thick and they can converge into smaller kind of smaller ribbons or thinner ribbons. And here, that's not the case in the skin. On the skin, they actually start out pretty tight right away. And then on the clicker, they behave a little bit different, a little bit different as well. So what are other benefits of this method, which are really cool benefits of this? So of course there's dynamic nature to all of this, right? Depending on how the character is oriented, depending on how you view it, like when you view it, things will look a little bit different. But another thing, because we are traveling basically in a depth buffer, we can travel across mesh boundaries and we can travel across UV seams because we are not unwrapping meshes based on UVs, right? When we're simulating, we're not dealing with any of that information. We're strictly in screen space on all geometry, right? So what that means is that a ribbon will grow from the chest to a shoulder. And it doesn't matter if there's a UV seam or not in there, right? It's just up to us whenever we're simulating a screen space and that information is fed to the CPU. At some point, we're gonna jump the UV seam, and of course that we need to determine on the CPU side. If we see like, all right, this ribbon was here in this UV location, and the next frame it's here, and it's a big jump, we should start a new ribbon instead of continuing the previous ribbon, of course. Otherwise, we don't want to be connecting huge. Like a ribbon across big UV space. Another great example here from mesh to mesh, that you will see how these the blood dripped from left knee here all the way onto the right leg here, and that would be pretty hard to do using traditional methods. Maybe like if we had, let's say we actually simulated this drip on a triangle and we knew all the 3D triangle positions. Even if we had adjacency data on which triangles in the mesh are adjacent to the triangle we're on, we wouldn't know which triangles are there that are not adjacent, right? So we would need to know as we're traveling, we actually need to analyze all triangles of the mesh, and that would just be very hard and potentially expensive, right? So doing it in screen space kind of allows us to circumvent all of that and just do it on depth buffer, and that's it. And it totally works. Here's the view of this kind of with UVs and the UV layout. You will see that we were simulating here in the UV space, and then we're like, oh, now we jump to here, and now we're just going to start a new ribbon here, and that is what's happening in this particular location. What else can we do? Well, we were talking about droplets before, right? With rain, we were generating water droplets. With blood, we can generate blood droplets. And just to enhance this again, we know that the droplet is blood, and as it simulates, we can intersect it with depth buffer, just little marks through a depth buffer to see whether or not the particle actually starts intersecting geometry. And with a couple of checks in the object ID, we can actually add blood into the render target where the droplet is hitting the character, right? So here's a little video, a little debug video of there's blood droplets falling off his chest, and as they land on his pants, there's little droplets showing up in the render target, right? The cool part about this, of course, it's all in screen space. It's not like every droplet ever generates going to intersect. It's only going to be if you see it. But the cool part about it is that it shows potential. It also shows that it's very cheap. That's the cool part about it. Is that it's very, once you can establish this system, it becomes easy. Certain things become fairly easy. And then they add this little detail, which is really cool. So, and to be even fancier, right? We can combine both systems, and if we could have things like water drips, sample, blood map, right? So if we have water drips on the character, you will notice on her as the water drips happen on this character, if they intersect bloody area, they pick up red tint, right? So this is two systems working. It's the blood system and the rain drip simulation system working together, where the rain drips are just gonna simulate on the surface as they were before, but they're like, oh, if I'm on a character and this character has a render target, let me just check if the location is bloody. And if location is bloody, I'm gonna pick up a tint and I'm gonna render myself a little bit more red into the albedo of the G buffer, right? So yeah, so that's pretty cool. That adds again another little detail. So really quick about the attachment, right? The thing is, we're talking about screen space attachment with the motion vectors. That works. It can fail, right? It can fail because it's just motion vector prediction correction based. If we're using object ID and if we know the triangles that the particle is on, we can certainly just store the information. If we know the triangle we're on, we can just store, okay, I'm on this triangle and this is the barycentric coordinate. And the next frame, whenever we updated the mesh and new location is there, we can just look up the newly generated position buffer, right, vertex buffer, and recompute the new position based on just barycentric and knowing the triangle ID, right? So that gives us perfect attachment. That gives us an attachment that works off screen and behind geometry. So that is an additional way to using the object ID to make these attachment much more robust. And we certainly use that wherever we could, right? So for the things that didn't have object ID, we could use the screen space tracking. If they did have object ID, we tried to use the triangle attachment. And then there's such things as LOD switches and so on, and then whether triangles do not exist because we switched to a different LOD, then we can fall back to the screen space attachment for one frame, recompute the information, and go from there. We can also just retrieve the skinning information, just redo the skinning. Potentially we could do that. Talking about the GPU to CPU events, because we can feed information from the GPU to CPU, and using the object ID, we can do things like this, where we have these drip particles, just these little particles falling down, intersecting with geometry. Wherever they intersect, there's rain splashes, GPU rain splashes spawned. But as well, you will notice that the character was actually flinching and playing a special gesture, and that's because because we know the object ID, we know what character it is, we can send an event saying, hey, you're having that many intersections with the water particles. You should play a gesture, and then on the script side, the designers would play a gesture. Other use cases, let's say there's a cool case with the snow. Snow falling onto the surfaces, falling onto the ground, falling onto the character. So that's cool. Just a little bit of detail. That if you notice, it's pretty awesome. Because of the information we have available, we will stick to geometry. We fall. The cool thing about snow, again, if it loses tracking, fine. It can disappear. It can fade out real quick, or it can just fall. Because we have information about skin or hair or cloth, we can do things like on the skin, it's going to melt a little bit faster. It's a lot of interesting effects we can do fairly easily once the system is set up. Here's the simulation of roaches kind of running around the geometry and hiding behind geometry or moving along the normals, which was done kind of with this GPU and screen space tracking and so on. They stuck to only kind of background geometry that doesn't animate, which made them obviously the tracking itself wasn't really that big of a deal because the geometry wasn't actually changing. But yeah, another one of those things, we move in screen space, we simulate in screen space, but we live in 3D space. A quick note, these shaders became pretty complicated. Ultimately, this screen space tracking and checks and whether or not you landed on where you landed, and especially with ribbons and how the ribbons grow and then living in the same wavefront and cross-lane access and all that, it becomes really complicated. And it's important to be able to debug. And we had a little logging system where we would log from GPU to CPU, and we could kind of rewind the game and look at what happened. That is extremely useful for this kind of a system. Without it, it would be very hard because there's so many different tests. We don't really know what exactly fails, why it's failing, why do these drips look this weird way. So debugging is extremely important if you were going to implement this kind of system. So in conclusion, well, we looked at several examples of what the screen space simulation has to offer. And the cool thing is that once we convert to screen space, there is just so much information available. And it's just a matter of being able to use that information in certain creative ways. So we had the rain splashes, we had snow, but we had the blood and the water, the rain drips and so on, right? And I'm sure there's plenty of other use cases for this where screen space can be used for simulation, and this object ID buffer could be used for just enhancement and additional effects. So I hope this was a interesting talk. I hope you enjoyed it. Naughty Dog is hiring, so check out our careers page for any positions, and definitely check out other